Hello friends, welcome to VK Lectures. In this lecture we are discussing the digital circuits where we are discussing about adders, which are half adders and full adders. Digital circuits. Any digital circuits can be categorized into combinational circuit and a sequential circuit. Now what is the difference between this combinational circuit and the sequential circuit is that if you consider three input A, B and C, and it's going through a circuit and it produces Y, and the property is that it does not have the feedback, which is, we know that Y will be a function of A, B and C, and in the next output Y will not go to the input. That is called no feedback. There is no feedback to the input side of this circuit. Another is no memory effect. Now after the first output, for example 101 is the answer that we have got, and the next output Y2 is a function of Y of Y2 will be a function of A, B, C, and these are different inputs and you have different Y, and the memory is, you already had an output here. This output will not affect the second input, which means the output does not contain any residue. Once it is complete, once the operation is complete, the system goes back to zero. System will go back to zero. There is no residue present. That is called memory. No memory effect is in the combinational circuit. Some of the examples are adders, subtractors, decoders, converters, multiplexers, comparators, ROM, read-only memory. Okay, likewise. Now just let us take the case of adders. You have two input A, B circuit, Y equal to A plus B. In the next output, what will be there? Input A dash B dash, Y is equal to A dash plus B dash. This is, let it be Y1, Y2. These two are independent parameters or independent results. Okay, so that is why it is having no memory effect, and since there is no feedback, this feedback is not there, so due to that it does not contain any feedback mechanism. So this is the example or the idea of combinational circuit, while the sequential circuit is the just the opposite. That output is the function of the input, and which means there is feedback exists, and as well as in some sequential circuit you have the first output Y1 equal to, for example you are given to add 1 0 and 1 1. Okay, 1 0 gives you 1 and 1 1 gives you 2. Sorry, it's 1 1 is 3. But after doing the first input you got Y1, this is Y2, so Y2 will contain some part of Y1 also, so it will be Y2 plus Y1. It can be anything, some half of Y1 or half of quarter of Y1, etc. But it will contain some function of Y1 also, so which means your next output Y2 will be function of AB, that are the input, present input, plus there will be a function of Y1, which is the previous output. So the next output depends on the previous output. So that is called memory effect, and that will be present in the sequential circuit. Good examples are flip-flop, registers, counters, multi-vibrators, bistable vibrators, that are astable, multi-stable or bistable we have already discussed, which means there is no stable state. Bistable means there are two stable states. And counters, yeah, monostable is also there. Here we will understand how to solve a combinational circuit. Now, solving the combinational circuit consists of few steps. First is to understand the statement given in the problem. So understand the statement given in the problem is the first task. Now after that, identify the input and output. There can be many input A, B, C and corresponding output, etc. It can be any number. Now then after finding the number of input you get in terms of 3 input and 2 output, just for example. Okay, then assign the names A, B, C, Y1, Y2, Y3 for the input and output respectively. Then is to construct the truth table. So corresponding to A, B and C, that is the input, you have to draw the truth table, keeping in mind the Y1, the functions of Y1, Y2 and Y3, and this can be based on the relation between the output and the input. Then design the K-map to minimize the Boolean expression. K-map is the better option to reduce to the Boolean expression. Now then we can design the logic diagram using logic gate. Here we have a question which asks to find the digital circuit corresponding to the output given. So let's start to solve this sequential circuit, the combinational circuit. So A, B and Y, this is the 2 input and the output given. 0, 0, 1, 0, 1, 0, 0, 0 gives 0, 1, 1 gives 0. Now we don't know according to the Y what is the circuit. So to that we will draw the truth table according to the Y. So this is how you can draw the truth table: A bar A, B bar B. In any form you can write, but let us stick to this form: A bar A, B bar B. So A, write down this, this is A bar, B bar, this is A bar, this is B, this is A, B bar, and this is A, B. So A bar, B bar is 1. So A bar, B bar, this is the only place you have high output. All others are 0. So 0, 0, 0. Okay. So A bar, B bar is the output. All other areas or all other output is 0. So according to the digital circuit or the output, Y is equal to, you can write it is A bar dot B bar, which means if you have an input A, it has to be negated, another input B, this also has to be negated, and this has to go through the uh, circuit or the gate, that is AND gate. So after moving through the AND gate, you will get A bar. So here you have A bar, here you have B bar. So A bar dot B bar. Okay, but many a time this option won't be there. So this is the circuit A. So here you will have A bar, this is B bar, and here you will get A bar dot B bar. But now the question problem arises in the options. Most of the time it won't be in this direct form. Sometimes you have to find out from the options also. So A bar dot B bar. Now here A plus B bar, A plus B bar is equal to, what is A plus B bar? Applying the De Morgan's theorem, we get A bar dot B bar. So instead of writing A bar dot B bar, you can also write A plus B bar, and that is nothing but it's an OR gate. So this is A, this is B, OR gate with an negation or the not. So this gives A plus B bar. So that's equal to A bar dot B bar. So both these digital circuits gives the same output. Any of the circuit you can select. So this is how you can build the digital circuit using the output of a given inputs. Another kind of combinational circuit is the adders. One used to add or sum to find sum, but in general this is not the algebraic sum, but the this binary digit addition. So it is called adders. So perform addition of n number of 1-bit form. Okay, so there are two kinds of adders. One is half adder and full adder. There is no relation between half and full here. It simply means that half adder has two 1-bit inputs, and while the full adder has 3 1-bit inputs. Okay, so half adder A and B, this is the sum and this is the carry. Here you have full adder. Full adder consists of 3 inputs and the sum and carry. This is carry. Here also we can write C is carry here on the right. So carry means for example, if you have 64 plus 86, so 0 1 7 1 5. So when I put 0 here, 1 is the carry, C value is 1, sum is 0. So carry means C. So 1 plus 7 plus 8, that is 15. So 15, I will write 5 here. Again 1 goes as carry. So new carry is 1. So likewise that is a function of carry. Yes, that's it in here. We have a question or to solve this half adder circuit. Now half adder circuit, we know there are 2 input sides and 2 output. 2 outputs are sum and carry. The inputs are A and B. So let us find the truth table now. So truth table says 0 0, it is sum. What is the sum? 0 plus 0 0 0. So since it is there is no need to go carry anything, so carry is also 0, and 0 plus 1, that is the second input, 0 plus 1. Sum is 1, so it gives sum 1, and there is nothing for carry forward, so as it is, carry is 0. Similarly, 1 and 0, 1 plus 0 is again 1, nothing to carry forward, so 1 0, and 1 1, 1 plus 1 is 2, but 2 cannot be written in this way because it is a binary number, so 1 0, so 2 is equal to 1 0, so this is sum. And what about this? This is carry, so sum is 0 and carry is 1. Okay, now let us put this into the Karnaugh map. A bar A, B bar B. Here this is okay, this is we will just write down what is this. 0 0 is 0, 0 1 is 1, 1 0 is 2, and 1 1 is 3. 0 1, 0 1 is 1. Now let us make the Karnaugh map here. That means sum I am writing it in the Karnaugh map or projecting it in the Karnaugh map. So sum is yes, so 0 0, so wherever there is 1 you have to mark here, so 1 1, that is 0 1 and 1 0, 0 1 1, 1 0 1, these two inputs are 0. So what is sum equal to? Sum equal to A bar B. This is, what is this? This is A bar corresponding to B, it is B, that means the other input, so A bar B plus, what about this? This is equal to A B bar, so A B bar. Now this output is nothing but A X or B, A X or B, that is exclusive OR. So this gate is nothing but exclusive OR, and this sum is provided by exclusive OR gate. Now let us look into the carry side. Yes, sorry, C. So just transfer the C to here. So wherever there is 1, put it as high input. So 1 1, 1 1, this is the only place where the carry is high. So 1 1 is this. So in all other region it is 0 0. So Y or C carry is equal to, what is this? A B. So carry is AB. AB means product, so it is AND gate. So by exclusive OR gate and AND gate we can give or produce the half adder circuit. So this is how you can produce the half adder circuit. So half adder A B, this is the XOR gate. Sum is given by A bar B plus AB bar, and here both of the input AB is going to the AND gate, giving C is equal to AB product AB A dot B. Okay, through this we will get the half adder as sum of that is, this is 2 output. Okay, this you cannot add this, but it will remain as 2 outputs. So S is equal to A X or B, and C is equal to A dot B. Now coming to the full adder. Full adder is very similar to the half adder. You have three input, one bit input, binary digits, and two outputs, sum and carry. So this is CAR carry. Okay, these are three different individual inputs. Okay, so now let us look into how we can solve this problem. First we start with the truth table. Then we will reduce the reduce to the using K-map. We will reduce, then we will draw the the circuit. We will build the circuit using the gates. Okay, let us fill the truth table. So this is the truth table, and three input A, B, C. This is sum, this is carry. Alright, so since there are three input, let us start with 0. This is 1, 2, 3, 4, 5, 6 and 7. These are the binary, the decimal number, and this decimal number are corresponding to each input. So 0, 0, 0 correspond to 0, 0, 0, 1, 1, 1, 0, 2. So likewise, so 1, 1, 1 means 7. Okay, so 0, 0, 0. If I have to add 0, 0, 0, sum I will get it as a 0. Carry, there is no carry. For 0, 0, 1, sum is 1. No need to carry anything, so it is 0. So 0, 1, 0. 0, 1, 0 means again 1 is sum, carry is 0. 1, 1. If you add 1, 1, you will get 1, 0. 1, 0 means carry should be 1 and sum should be 0. Now 1, 0, 0, again sum is 1, there is no carry, and 1, 0, 1, the previous one, that is sum is 0, carry is 1. 1, 1, 0, again 0, 1, 1, 1, 1. 1, 1, 1 gives sum. What can be the sum? 1 plus 1 plus 1. Yeah, 1 plus 1 is 2, 2 plus 1, 3. 3 means, what is 3 equal to? 3 equal to 1, 1. So carry is 1, sum is 1. So sum is 1, carry is 1. Now for sum, let us find the truth table corresponding to the sum. So A bar A. Now start with B bar C bar, B bar C, BC and BC bar. This is the order that we have to follow. One change in the digit is allowed as you move through the Karnaugh map. So okay, so according to that, A bar corresponds to 0, A 1, B bar C bar 0, 0, B bar C is 0, 1, BC 1, 1, B C bar 1, 0. So likewise we will put the decimal numbers 0, 1, this is 0, 1, 1, 3, this is 0, 1, 0, 2, this is 1, 0, 0, 4, this is 1, 0, 1, 5, 1, 1, 1, 7, 1, 1, 0, 6. So this is regarding the sum. So wherever there is 1 output, mark it as high. So here 1, 1. So let us write the find it here. So 1 1, so sum is 1, so here you can put 1. Again 1, where do you see? Here you have 1, that means 2 is also 1. Okay, now 1 is here, 4 is 1, so 4 is 1. Now 7 is 1, so 7 is 1. In all other input, sorry, all other input is corresponding to the sum is 0. That means sum output is 0 in all other cases, and we have marked 1 1 1 1. Now let us write what are they. So this is starting with A bar, B bar C, so A bar, B bar C, that is our this one. Then we have here A bar, B C bar, so plus A bar, B C bar plus A B bar C bar. So here we have A B bar C bar plus here A B C, right? Now let us look into this. You have A bar common. When you take A bar common, you have B bar C plus B C bar. Now plus again you have A common here, which gives leave us with B C bar plus B C. Now this is A bar, and what about this? B bar C plus B C bar is B X OR, that is exclusive OR of, that is A B is equal to A B bar plus A bar B. So how do we write that? A X OR B. So this becomes B X OR C. So that is the first term, plus A into, what about this? B C bar plus B C. Now exclusive NOR says of exclusive NOR of A comma B says AB plus A bar B bar, that we will write it as A X or X NOR B, or it is equal to the NOT of XOR. X NOR is nothing but the NOT of XOR. So A XOR B whole bar. So let us write it as this is B C bar, so B X NOR C, which we would write it as A B X OR C plus this is A bar B X OR C plus A into this. I am writing it as in this form, B X dot, it is B X OR C whole bar, right? Now this, if I assume it as A bar X plus A X bar, where X is B X or C. So again this is A bar X plus A X bar is nothing but A X or X. Now what is X? X is equal to B X or C. So that gives us A XOR X is B XOR C. So that is what our sum is equal to. Sum is, so you need two XOR an XOR gate with 3 input A, B and C. That is the sum of this full adder. So full adder's sum is given by A XOR B XOR C. Coming to the carry, carry has these values we have already seen. So wherever there is 1, there is so let us write down what are the numbers: 0, 1, 2, 3, 4, 5, 6 and 7. So 3, 5, 6, 7. So 3, 5, 6, 7. Now since this is a Karnaugh map, we can reduce by taking the different groups. We can make the group like this. The first group, the second one, I'll give it some other color. So here we have second group, and the third one, let's give some blue. So this is the third group. So in the first group, which is the green, BC and what will remain? A bar A. So it consists of A bar and A, and this is BC. So BC will remain plus, and in the first group A will be there. So BC bar and BC. So B bar and B bar gets cancelled. B and B bar gets cancelled. C will remain. So it is AC plus, and in this third group A will remain. Along with A, here you have C and C bar will go, B will remain. So AB. So now we have, you can write like AB plus BC plus AC or CA. So it's just like having some terminal. So the carry is a product. So here CRRY, carry is a product of AB, BC and AC. So which means you need 3 AND gate. And for sum, we have seen we need XOR gate with 3 input. 3 input. So let us draw the curve. Draw the circuit. So this is the full adder, which has sum equal to A XOR B XOR C, and the carry equal to AB plus BC plus CD. So here we have ABC, and all ABCs are going to the XOR gate here. So this is XOR gate, and sum you will get it as we already said, A XOR B, and here 3 AND gates are present, and and this all three AND gates are being fed to the OR gate, which gives carry CAY equal to, so this first one is here C and B, so this is BC, here it is B and A, so AB, and this would be A and C, so this is AC. So carry is equal to AB plus BC plus AC or CA. So this is sum and carry, and this is the circuit for a full adder, where you have to use the digital circuit in the form of XOR and OR.